is nothing but the column. So before going into the design procedure of a compression member, we should be aware of the main design criteria, assumptions that are used in the design. Okay, so main criteria, what are all the main design criteria used in the design of compression member? Allowable compressive stress sigma AC and slenderness ratio lambda, and assumptions. So to every theory, to every problem, there should be some assumptions. So here is the assumption that ought to be kept in mind before designing a compression member. So the member should be, according to the assumptions, the member is perfectly straight and the modulus of elasticity is constant in a build-up compression member, and the secondary stresses, which may be of order of 25 to 40% of the primary stresses, are neglected. And here is the design procedure of a compression member. So what is the first step to be done? We have to fix the allowable compressive stress. The allowable compressive stress sigma AC is 60 to 85 megapascal in the case of struts, and it is 85 to 110 megapascal in the case of columns. And the step 2 is to find the required area. How much area is required to design a compression member? So the area required is found by computing P by sigma AC. What is P? P is the load of the member, sigma AC is the allowable compressive stress. And the third step is like choosing a section from the steel tables. We have to choose a trial section whose area should be greater than the area required, and that chosen from the steel tables SP6 of 1. The step 2 is the finding the effective length. So how will you find the effective length? It is purely based upon the restraint conditions. Restraint conditions will be provided. From that we have to find the constant of, that is K, and we have to find the effective length L effective, and then slenderness ratio lambda. The step 5 is check for lambda. Check for lambda is nothing but finding the lambda and calculate the allowable compressive stress sigma AC from IS handbook. So lambda should satisfy the condition that is provided in IS 800/2007. Step 6 is load carrying capacity of the member. We have to check whether the load carrying capacity of the member can bear the load that is provided. So calculate the load bearing capacity from the allowable compressive stress and the area provided. And the step 5 is for check for safety. If the load carrying capacity is more than the applied load, then it is found to be safe. And if it is not greater, we have to reconsider the section, that is redesign the section by we have to redesign by choosing some other section, some other trial section. Here is the problem, how to design a compression member. There is a problem like design a compression member, that is column of I section whose length is 3 meter and it should carry axial compression of 300 kilonewton, that is the load on the member is 300 kilonewton, and the column is effectively held in position at the both ends and not restrained against rotation. Assume the steel conforms. So given data is like length of the member, it is about 3 meter and the load on it P is 300 kilonewton, and the support condition held in position at both ends but not restrained against rotation. Step 1 is fixing the allowable compressive stress. Since it is a column, we have to fix a value that is greater than 85, should be less than 110 megapascal. So we are taking it as 85 megapascal. The step 2 is finding the area required. Area required is P by sigma AC. P is 300 kilonewton, that is given, and sigma AC is 85 megapascal, which we have assumed. So from that we can find the area required. And then the step 3 is the choosing a trial section. This section is chosen, that is ISHB 250 is chosen based upon the area. Here the area is 6496 mm square, which is greater than the area required. And then the properties RYY, RXX, D, P, BF, TW, TF are taken from the steel tables. And the step 4 is finding the effective length of the column. So effective length is found by K by using the formula K into L. K is the constant that is obtained from IS 800/2007 page 45. It is purely based upon the restraint conditions. So we have found the L effective value, and the step 5 is finding the lambda, slenderness ratio. Slenderness ratio lambda is equal to KL by R minimum. K is the 1 and L is the 3000 mm and R minimum is 54.9, which from which we can get the lambda value as 54.6. From that 54.6 we have found the lambda value, and we have to consider some other factor like h by bf, which is less than 1.2, and tf 9.7 mm, which is less than 100 mm. Therefore, from the table 10 page 44 of IS 800 2007, it is found to be the buckle in class B or class C. So this buckling class C, B or C is purely based upon the minimum radius of gyration. We have to consider the minimum radius of gyration. So RYY is minimum 54.9 mm. From that, assuming E value as 250, we have found the FCD, design compressive stress, as 175.5 Newton per mm square. From that design compressive stress, we can find the allowable load. So allowable load FCD into A is equal to FCD is 175.5 Newton per mm square into, and area 6496 mm square. From that we get 1140 kilonewton, which is much more greater than 300 kilonewton, and it is found to be safe. Thank you for watching the video.